Welcome back to the Deep Dive. Today we're tackling something pretty amazing in AI, actually.
Well,
How is it possible that teaching a computer to spot, say, a cat online? How does that relate to detecting something as critical as cancer on an X-ray?
it sounds completely unrelated, but the connection is this powerful idea called transfer learning. Basically, instead of building every single AI model from scratch, which is, super expensive, takes ages.
Right. Massive amounts of data, huge compute power.
Exactly. So we take a model that's already like a master at a big general task,
Mhm.
identifying millions of objects, reading tons of text, and we cleverly reuse that knowledge. We repurpose it for something totally new and specific.
It's like the ultimate AI shortcut. The source we looked at mentioned cutting effort by maybe 80, even 90% sometimes.
Wow.
And that shortcut, well, it changes everything about who gets to use advanced AI.
Yeah.
Historically, building those huge foundation models, the ones with billions of parameters, that was pretty much just the domain of a few giant tech companies.
The ones with the massive server farms and data lakes. Precisely. Transfer learning opens that door much wider. It really levels the playing field.
Okay, so why does this matter for, someone listening, maybe working on a real-world problem?
Well, it tackles three huge roadblocks all at once. First, there's data scarcity. If you're, say, a medical researcher, you just don't have millions of perfectly labeled cancer images like Google has cat photos.
Right, that specialized data is rare.
And second, compute costs. Most organizations, universities, startups, they just can't afford the cost of training those enormous models from zero. It's prohibitive.
Okay.
And finally, there's time. Getting from an idea to a working AI solution. Transfer learning makes that cycle way faster, dramatically faster.
So our mission today is to really get into the nuts and bolts of this knowledge reuse. We want to look under the hood of the neural network, use some helpful analogies, make it all clear.
Yeah, the goal is that you walk away not just knowing what transfer learning is, but really grasping how that knowledge actually gets transferred from one place to another.
Okay, so let's start with an analogy. You had a good one.
The bicycle one. Yeah. Think about learning to ride a bike. You master the core skills, right? Balance, steering, just basic coordination. That's foundational knowledge.
Okay.
Now, later on, you decide you want to ride a motorbike. You don't have to relearn how to balance, do you?
No, that part comes naturally.
Exactly. That initial bicycle knowledge, it just transfers over instantly.
Mm.
You only need to learn the new specific motorbike stuff, the clutch, the gears, the throttle.
So the bike skill is the pre-trained model. The motorbike is the new specialized task.
You got it. That's the core idea.
Okay, that bicycle analogy really helps. And it leads us right into some key terms we need to nail down. Because people often mix up transfer learning and fine-tuning. They sound similar.
They are definitely related, but the goal is different, and that difference is important. Transfer learning TL, which is our main focus today, is about taking that core knowledge and applying it to solve a completely new problem.
Like the cat model being used for medical images.
Exactly. Or, taking a model trained on millions of general photos and using it to identify rare types of plants. The core task is changing. You're solving a different problem than the original one.
Okay, so that's TL. What about fine-tuning then?
Fine-tuning is more about improving performance on the same task, or maybe a very, very similar one. So imagine you have a general model that detects objects,
Okay.
but you specifically want it to be better at spotting cars, maybe in really bad weather like fog or heavy rain. You'd take that existing model and fine-tune it using a smaller data set focused just on cars in those tricky conditions.
So you're not changing the basic job, detect objects. You're just making it sharper for a specific scenario, cars in bad weather.
Exactly. TL is about changing the context, shifting the problem. Fine-tuning is more like polishing the performance for something it kind of already knows how to do.
Got it. TLRO, context shift, fine-tuning, performance polish. Okay, now the source material we looked at mentioned different types of transfer learning. Inductive, transductive, unsupervised. Why do we need these extra categories? If I can just adapt my spam filter from English to Spanish, isn't that just transfer learning?
That's a fair question. The reason for these distinctions, inductive, transductive, unsupervised, is mainly strategic. It helps developers figure out the best way to approach the transfer based on what exactly is changing between the original problem and the new one.
Okay, so it guides the how-to.
Right. First, inductive transfer learning. This is where the kind of data stays basically the same, let's say, medical images, but the task itself changes. Maybe the original model was trained for just general X-ray analysis, and now you want it to specifically find, I don't know, rare bone fractures. Same data type, different goal.
Okay, data same, task different.
Then you have transductive transfer learning. This is your spam filter example. The task is exactly the same, detect spam, but the domain, the context, changes drastically. You're going from English emails to Spanish emails, the underlying language, the data distribution, it's all different.
Task same, domain different. Makes sense.
And the last one, unsupervised transfer learning. This is a bit different. Here, both the original task and the new task work with unlabeled data. The model is just learning general patterns or structures, maybe like picking up the rhythm or mood in music without needing lyrics.
So it's learning underlying patterns without explicit labels.
Exactly, and knowing which of these categories your problem falls into helps you decide later on which parts of the pre-trained model you might need to adapt or unfreeze, as we'll get to.
All right, let's get into the really cool stuff now, the mechanics. How does this actually happen inside the AI? How does a network trained on, I don't know, bananas and buses somehow become useful for medical diagnosis?
It really comes down to the architecture, the layers inside the neural network. We often call it a feature factory.
A feature factory. Okay, I like that.
Yeah, it takes the raw input, like the pixels in a photo, and step by step, layer by layer, it transforms that raw data into more and more meaningful features, more abstract concepts.
So it builds understanding progressively.
Exactly. Let's stick with image recognition. The very first layers, the bottom or early layers, sometimes called the stem, they're like the model's basic visual cortex. They learn really simple, universal things.
Like what?
Basic edges, corners, simple textures, maybe color blobs, stuff that's fundamental to any image. And the key thing is, this knowledge is highly reusable. It doesn't matter if it's a cat or a car or a cancer cell, edges and textures are still relevant.
Okay, so that's like learning the absolute basics of seeing.
Uh-huh.
The visual alphabet.
Perfect analogy. Then, as you move up into the middle layers, the network starts combining those simple features to recognize more complex shapes and parts of objects. Things like the curve of a wheel, the shape of an eye, maybe a specific pattern on a leaf.
More complex components. Are these as reusable?
They're somewhat reusable. It depends. If your new task involves objects with similar kinds of shapes or parts, then yes, this knowledge is still very valuable, but it's less universal than the basic edges and corners.
Right.
And finally, you get to the top or late layers. These are the ones that assemble all those parts and shapes into recognizing whole objects. That's a dog, that's a bicycle, and the very last layer, the one we call the head, makes the final decision or classification. This image contains a cat.
Okay, and those top layers, especially the head, they're specific to the original training data, right?
Exactly. They've learned to recognize those specific objects the model was originally trained on. So for a new task, these top layers, and especially the head, are usually not reusable. You typically throw them away and replace them.
This layered structure is fascinating. So we keep the deep early layers because they hold general knowledge, and we swap out the top task-specific layer. What are the terms for those two main parts again?
We call the reusable part the backbone. That's all those early and middle layers doing the general feature extraction, edges, textures, shapes. And the part you replace, the task-specific bit at the end, that's the head.
Backbone and head. Got it. And the magic of transfer learning is keeping that big pre-trained backbone largely intact.
That's where the massive savings in time and data come from. You're leveraging potentially millions of dollars worth of prior training. Okay, so you've got your pre-trained backbone, you've popped on a new randomly initialized head for your specific task. Now comes the really crucial decision. What parts of that old backbone, if any, should you let learn and adapt to your new data? We call this unfreezing layers.
Unfreezing, meaning you allow them to change their weights or learn parameters during the new training process.
Precisely. You're letting them adjust based on your new, smaller data set.
Okay, let's use that music band analogy again. The backbone musicians know the basic tune. The head is the new lead singer for this specific song, or new task. So unfreezing is like letting the original musicians improvise a bit to match the new singer.
That's a great way to put it. And the big question is, how much improvisation do you allow? Let them go too wild, and they might forget the original melody that was actually useful.
Ah, okay. So getting that balance right dictates the whole training strategy.
Absolutely. There are sort of three main strategies, and which one you choose depends heavily on how much new data you have and how different your new task or domain is from the original one.
All right, what's strategy number one?
The simplest, fastest, and generally safest approach is to unfreeze only the head. This is also called feature extraction. You keep the entire pre-trained backbone completely frozen, locked down. It acts just as a fixed feature extractor.
So the original musicians play exactly what they always played, only the new singer learns.
Exactly. This works really well when you have a very small new data set, and the new task is very similar to the original one. Think like going from classifying different dog breeds to classifying different cat breeds. Low risk, very efficient.
But what if my new task is quite different? Like going from everyday photos off the internet to, say, grainy medical scans or maybe satellite images. Just changing the singer might not be enough.
Good point. In that case, you need more flexibility. That brings us to partial fine-tuning. Here, you unfreeze the new head and maybe the last block or the last few layers of the backbone.
Okay, so you let the singer learn, and maybe the lead guitar and drums improvise a little bit, but the core rhythm section stays the same.
Perfect. You keep those really fundamental low-level features, the edges, the textures frozen because they're almost always useful, but you allow the layers that learned more complex shapes and parts to adapt a bit to the specifics of your new data, like the different resolution or noise patterns in medical scans. It's a balanced approach.
And the third option sounds like the riskiest one.
It can be. That's full fine-tuning. Here, you unfreeze the head and a large portion, maybe even all of the backbone layers. This gives you the absolute maximum flexibility to adapt the entire network.
When would you do that?
It's best suited for situations where you have a large amount of new data, or when there's a massive difference between the original domain and the new one, like going from photos of cats to analyzing complex financial charts, perhaps.
But what's the big danger here? You mentioned forgetting the tune.
Exactly. The major risk with unfreezing too much, especially with limited data, is something called catastrophic forgetting. The model gets so focused on learning the new task that it overwrites. It basically destroys the incredibly useful general knowledge it had in those lower layers. The musicians completely forget the original song.
Ouch. So how do the pros avoid that? The source material mentioned a kind of two-stage approach.
Yes, that's a very common and effective technique, especially when doing partial fine-tuning. It's clever. Stage 1. You train only the new head for a while. You let the new singer learn their part first. And often, you use a relatively high learning rate. LR here. Let them learn quickly.
Okay, get the head working first, then what?
Then, Stage 2. Once the head is reasonably good, you then unfreeze the last few layers of the backbone that you decided to adapt. And crucially, you continue training, but now with a much, much smaller learning rate. Sometimes 10x, even 100x smaller than the head's initial LR.
Ah, so you let the musicians adapt, but very, very cautiously. Gently tweak their performance rather than letting them rewrite the whole thing.
Exactly. And that leads right into this idea of discriminative learning rates. It's like having different volume knobs for different parts of the network. The head gets a higher LR, learns faster. The deeper backbone layers get a tiny LR, learn very slowly and carefully.
Why is keeping that backbone LR so low absolutely critical?
Because if you hit those deep foundational layers with a high learning rate when you only have a small new data set, they'll immediately overfit to your specific examples and boom, catastrophic forgetting. The low LR forces them to make only subtle adjustments, preserving that precious general knowledge while still allowing some adaptation. Choosing what to unfreeze and how fast it learns, that's the real art of effective transfer learning.
Okay, so transfer learning isn't just this one monolithic technique. It sounds like it's really evolved. The source mentioned several sort of advanced flavors that push things even further.
Yeah, the field is always moving, always looking for ways to be more efficient, use less data, get smaller models, all that good stuff.
Right. One technique mentioned was knowledge distillation. Katie, how does that work?
Katie is pretty neat. You have a big, powerful, maybe complex teacher model that performs really well. Then you use that teacher model to train a much smaller, simpler student model. The student tries to mimic the outputs or even the internal workings of the teacher.
Oh, like a master chef teaching an apprentice. The apprentice learns the complex dish, but can maybe make it quicker or with less fancy equipment.
Exactly. The big benefit is you end up with a smaller, faster model that captures much of the performance of the big one. This is great for deploying AI on, say, mobile phones or other devices with limited resources.
Makes sense. And then there are these super efficient methods like adapter-based techniques. The source mentioned LoRA.
Right. Low-rank adaptation and similar adapter methods are really popular now, especially with large language models. The idea here is genius. You keep the entire massive pre-trained backbone completely frozen. Billions of parameters untouched.
Okay. So how does it learn?
You insert tiny little extra modules called adapters next to or within the layers of the frozen backbone. And you only train these tiny adapters. They might have, maybe only 1% or less of the parameters of the main model.
Wow. So you're just training these little add-ons.
Yeah, it's incredibly fast and memory efficient because you only need to save and load these small adapter weights for each specific task, not the whole giant model.
That sounds incredibly practical. What else? The source talked about zero-shot and few-shot transfer with foundation models.
Ah, yes, the giants. These are the huge models like GPT-4 or large vision models. They've been pre-trained on such vast and diverse data sets like a huge chunk of the internet that they often have an uncanny ability to perform new tasks that they've never been explicitly trained on with zero or just a handful of examples.
Like the polyglot analogy, the genius who can pick up a new language almost instantly just by hearing a few sentences.
Exactly. They have such a broad base of knowledge that they can generalize incredibly well. Think of models like SAM from Meta AI that can outline almost any object in an image without specific training for that object type.
Impressive.
Yeah.
And one more, cross-modal transfer learning. Sounds complex.
It can be, but it's powerful. This is about combining information from different types of data, different modalities. So maybe you combine text features from a doctor's notes with image features from an X-ray scan.
Ah, like reading subtitles while watching a foreign film. You're using two different streams of information.
Perfect analogy. For complex problems, especially in fields like medicine or finance, combining insights from text, images, audio, sensor data, that can often lead to much better results than relying on just one type of data alone.
So a whole toolkit of advanced techniques. But even with all this power, things can still go wrong, right? The source mentioned a common pitfall when fine-tuning.
Oh, absolutely. It's something almost everyone runs into when they start. You need to watch your training curves carefully.
What's the warning sign? What should you look out for?
The classic symptom is this. Your training loss is going down beautifully. The model seems to be learning the training data really well, but your validation accuracy, how well performs on data it hasn't seen before, it either flatlines or it actually starts getting worse.
Uh-oh. So it's acing the practice test, but failing the real exam.
Exactly. The problem is almost always overfitting. The model hasn't learned the general patterns. It has basically just memorized the specific examples in your training set, including all their noise and quirks. It can't generalize.
And the fix for that is usually dialing things back.
Pretty much. You need to increase regularization, maybe add techniques like dropout, which randomly switch off neurons during training to prevent over-reliance on specific paths. Or, often the simplest fix in transfer learning, just go back and freeze more layers in the backbone. Don't let it adapt quite so much to your specific, potentially small, training set.
Oh.
So if we want to tie this all together for someone listening who's thinking, okay, how do I actually do this? We can boil it down to a quick decision guide based on your resources.
Okay, a practical takeaway.
Right. If you've got small data, the domain shift isn't huge, like cats to dogs, and you have low compute power, play it safe, train only the head, feature extraction, fast, low risk.
Makes sense. What if you have more resources?
If you're lucky enough to have large data, and you can handle any domain shift because you have plenty of examples and you have high compute available,
Wow.
then you can go for full fine-tuning. Aim for the best possible performance, but watch out for that catastrophic forgetting.
And what about that middle ground or situations where efficiency is absolutely paramount?
That's where those newer methods shine. If you're in any situation with very low compute, or you need super fast deployment, or want to handle many tasks without storing huge models, definitely look into those adapter-based methods like LoRa. They offer a fantastic trade-off.
So ultimately, transfer learning is this powerful art of reusing knowledge. It saves huge amounts of time, compute power, and crucially, data, which is often the scarcest resource.
Absolutely. And it's not just for images. The source materials strongly emphasize that these concepts, the layered structure, the transferability of knowledge, apply just as much to language models and NLP.
Right. A model trained on billions of web pages can be quickly adapted to summarize legal documents, translate medical texts, or power a specialized chatbot.
The same principles apply.
So if you're listening and you're working on a specific AI problem, or you just want to get deeper into the practical details, maybe see the full cheat sheet comparing strategies, or explore related areas like generative AI or prompt engineering that build on this, we really encourage you to check out the source material. We've linked it for you.
Definitely worth a read. Thinking about this layered structure of neural networks, it offers a really interesting lesson, maybe even beyond AI. It shows that fundamental knowledge, the basics like edges and shapes or basic grammar is universal and incredibly valuable to reuse.
But the high-level application, the specific skill, that head layer, is always task-specific. It needs focused development for the new goal.
Right. So the provocative thought maybe is, how can we apply that idea of layered learning to our own lives, our own professional development? What's our foundational backbone knowledge that we should protect and reuse across different roles or projects? And what new task-specific heads do we need to be actively building right now to tackle the challenges ahead?
That's definitely something to think about. A great place to leave it. Thank you for joining us on this deep dive.